Hi everyone, welcome to the session. Basically today we are doing a discussion on like analog circuit. Basically on like the what will be the ideal voltage source, current source, some RC circuit and their time constant, their time domain and frequency domain analysis, like intuitive analysis. Okay, so I feel you will all enjoy this session. So let's start. Okay, so actually I am starting. Then
Let's start.
Srijan will talk about some okay circuits and system. Okay, so okay I will share my screen. Okay, it is visible, right?
Yes, it is visible.
Actually okay, we can do another thing like mm actually if we have a whiteboard na in the Google Meet, so you can also write Srijan. Okay, so I am creating a
Okay.
whiteboard. Okay, okay, 1 minute. Okay, I have pasted the link. Okay, you can
Yes.
you can see in the like in the message comment section. Okay,
Should I open it or not? Should I open it or not?
okay, open it. Are you on the whiteboard right now?
Yes.
Can you? Okay, I am writing something. Okay, if you can see, please let me know. Okay, so this is the pen. Okay, is it visible?
Yes. Yes.
Okay, so let's try. Okay, so now, so what is a voltage source? Okay, ideal voltage source. So the symbol is like this. Okay, so let's say this is V voltage. This is the ideal like the symbol of a voltage source, and the symbol of a current source like this. Okay, let's say this is the I. So now for an ideal voltage source, what will be the IV characteristics? We all know that. So if this is I, like we are finding the voltage versus the current through this. Okay, let's say this is IV. So this is IV,
Okay.
and we will further try the current source. This is the current source, and we will find the voltage across this. Okay, thus there will be two waveforms. So for an ideal voltage source, the the voltage source try to maintain the same voltage across it, whatever the current, like the current may be anything, but the voltage remain constant like V. Okay, so let's say this is VL.
Yes.
Okay, so the waveform will be looking like this, the characteristics. So we can see that the voltage at this node is okay. So this is wrong, right? So this will be our
Yes.
okay. 1 minute.
Voltage should be on the y-axis, right?
Yes. So okay, I can do this, right? So let's say this is a positive voltage. Okay, so the oh, so this will be the case. Okay, so the
Yes.
current may be positive here or current may be negative here, the voltage remains constant. This is nothing but VL.
Remains same.
Okay,
Yes. Voltage
this
remains same always.
yes, this is the property, like the IV characteristics we can say. And we are modeling this as like this. So for a ideal voltage source, we are assuming there is a series resistance of Rs, and the for ideal case this value of the series resistance is 0 ohm. Okay, for ideal case.
Yes.
Okay, so this is the property. Now similarly, so Srijan will do this. Okay, so this will be our I
Okay.
naught and this will be our V naught. Now we have to do what will be the IV characteristics of a ideal current source. You can use next page as well, Srijan. Okay, so we can make this pages. Okay.
Okay. But for me, it is view only case.
Oh, view only.
Yes.
Actually, I
You
have.
have to give me the edit access, I think.
Okay, yes, yes. So you can do now. Okay.
Okay.
This whiteboard is slow, so forget it and do according.
But where can I get the pen, or
Pen,
it is not
left
visible
side,
here?
left side. Okay.
But till now, it is visible here on the view only case.
Okay, you can refresh it once. Refresh it.
Okay. Okay.
Ah,
Okay. Just a minute.
okay, okay.
Yes. Yes. I get it. Yes. If it is ideal current source, then current should be same across all case. It is right
Yes, yes.
or not? Voltage may be anything,
Yeah,
but if I
voltage can be anything like from minus infinity to plus infinity. The current remains same.
current remains same, so I think it is like this.
Yes. And if we model the current source with a resistance, what it will be.
Okay. So can I go to next page?
Yes, yes, yes.
Okay. Wait a little bit because I am not used to use that thing.
Okay, okay, no problem.
So it is visible or not?
Page number 2.
No, no. I am doing this on this page.
Okay, okay, do. It is visible. Okay.
My drawing is uh, not good, but
Okay, okay, it is fair enough. Okay. Everyone will understand.
okay. Uh, I I not think are is it right or not?
Yes, this RS is ideally infinite. Okay. So
Yes.
that we are telling that no current can go through this resistance. Okay. So this IRS will be 0. Okay, ideally. So that all of the current can, well, like, will flow through this branch only. Okay, no current can go through this RS resistance, like the parallel resistance, right? So that our
Yes.
IV characteristics will be looking like this. Okay, so this is the case.
Yes.
Now another thing we will discuss, like we have plot the IV characteristic. Now if we, like, go to the second page. Okay.
Okay.
Hmm. Now if we try to plot V V voltage, like the for the voltage source case, versus time, what will be the picture, like what will be the waveform? Like we want to plot the voltage of a voltage source with respect to time, then what it will be. And similarly we want to plot current versus time for a ideal current source.
Yes.
So this will be like this, right? So time may be minus infinity to plus infinity, the voltage
Yes.
remains constant, right? So this will be like this,
Yes.
and this is our positive Vx. Okay, so this is our
Hmm.
positive Vx.
Okay.
And similarly this will be like this will be our positive I naught. Let's say Ix. Okay, the value is Ix,
Yes.
right? This is okay, right?
Yes. Yes. Yes.
Okay, now Sijon, we will go to two port network. Okay,
Okay.
so can you please elaborate this?
Okay. So I am in the third page.
Yes. Okay.
Okay. So is it visible or not?
Yes, yes, visible.
Yes, yes.
So correct me if I am wrong. So if there is any circuit like this, and it has two port, means it should have one input port like this and one output port like this.
And we are considering about the linear circuit. Okay, linear time invariant. Okay.
Yes.
Okay.
Yes. Yes. Or LTI system.
Yes, yes, for LTI. LTI. Hmm.
Yes. Amit, you can elaborate something
Okay.
like.
So two port means a port means two nodes. Okay, a port means two nodes. So two port means four nodes, right? So this is a, let's
Yes.
say, node one, and this is node one dash, and this is node two, and this is node two dash. Okay. So this is a
Yes.
port one, like let's say input port. Okay, input port, and this is output port.
Output port.
Hmm. And we know like the two most important electrical quantities our voltage and current.
Current.
Correct.
So if we do like the combination of this, so for this input and output port, so this can be voltage current voltage, or current, right?
Current.
Fine.
Yes.
Yes.
So and generally what we do for our circuit or system analysis, we generally like one of like the for a for one port, we make one of the nodes is ground. Okay, for easy calculations, like in our circuit. Okay, basically this is the model.
Yes.
We can apply anything to these four nodes. Okay.
Okay, so two port means there will be four node. Two will be at the side of input and two will be at the output, right?
Yes, yes, yes.
Yes.
So or what should I say about this two port network, like how?
I think you should give an example, right? Any component, and it is expressed as a two-port network.
Okay, okay, let's have a resistive circuit. Okay.
Yes, yes.
Okay,
I think that would be very useful for us.
so this is a resistor, right? This is having two port, right? On and on dash.
Yes.
Now, what like can we do this? If we apply a voltage source there, let's say the value is Vx, and this voltage is V1 and this is V1 dash, right?
Mm.
So we know that the V1 minus V1 dash is nothing but our Vx voltage.
Yes.
Now we can find here the current. What is the current flowing through this resistance?
Vx by R.
Yes, we know the this voltage minus this voltage divided by this resistance will be this current, like in this
Current.
direction, right? The current will
Yes.
flow in this direction. So here I is nothing but so this voltage is nothing but V1 and this voltage is nothing but this voltage, this is V1 dash. So
V1.
and the difference is nothing but Vx. So I will write directly this, right, Sijon?
Yes, yes.
So now for two port case, what I can do more? Like we know this is a two port, right? Sorry, this is a one port network. This element,
Yes.
this is a one port element.
Only two nodes are there.
Only two nodes are there, right?
Yes.
Okay. So this is the model. Okay, you need to know the two port network very like concretely, I would say. Okay.
Okay.
Yes.
So Srijan, can we go like RC circuit? Like this is like
Yes.
okay. Go to the RC circuit. Okay, like RC, RL, and RLC. Okay.
One thing, I think we should discuss some basic KVL in two-port
Yes,
network.
yes, yes. Okay, okay, okay,
Like
okay. You
when in two-port network, I think we should consider it ground or not, if KVL is applicable or not. This type of question,
okay,
if
okay.
you
So
have.
you can start. I will continue. Okay. Like the thought in your mind, which having in your mind. So you can start. I will continue there.
Okay.
Go to the fifth page.
Oh, right. It is visible.
Yes, yes.
Yes.
Okay. Like there is some voltage called P1,
Okay.
and there is another case. Like there is in picture one, this is capacitor is C1 and here is C2
Okay.
also P1.
Okay. Okay. I understand your thought. Okay. Like the grounding thing or without grounding thing.
Yes, yes, yes.
Okay.
I think this is grounded.
Hmm. Okay.
I mean, what is the difference between these
Yes. Yes.
uh,
Yes. Yes.
two ports? Yes. Yes. I, I mean, I think you got it right.
Yes. Yes. So basically, we can take the output from here. Okay. For the both two
Yes,
cases.
yes,
Okay.
yes.
So for this
What
figure.
is the difference between two these network? I
Okay.
mean,
Ha. So the circuit will behave same. Like only one difference is there is a ground here, but there is a not ground here. Okay, like ground means there
yeah,
this potential is zero voltage. Okay, and in
yes,
this case this potential is not zero volt. Okay, like we cannot
zero volt.
100% sure there is a zero volt present. Okay, not 100%
Yes,
sure. this voltage can be anything, but according to that, this voltage has to be fixed due to this V1. Okay,
Yes, yes,
like the, let's say this is a V plus and this is, let's say, V minus. So whatever the, like the, this V1 is fixed, okay, due to the ideal voltage source concept. So this V1 is always this V positive minus V negative. Okay, so this
yes,
can
yes.
be 0, this can be 5, this can be minus 5, this can be minus 10,
Or
whatever it
something.
is.
Yes,
So
yes,
accordingly that this voltage will be fixed. Okay, due, like, according to this value. Okay, let's say this V1 is 5 voltage. Okay, now
yes,
let's make
yes, yes.
the,
Consider this V1 is one case in 5 volt, one case minus 5 volt for
okay,
both cases.
okay, then we will, okay, so first case, let's say
Yes,
this is case 1. So
yes, yes.
V1 is
5
5
volt.
volt. So now here let's say V minus is, let's say, minus 1 volt. Okay,
Okay.
this V minus, okay, this V minus we are having
Yeah, yes, yes,
minus 1 volt. Then what would be the
yes, yes.
voltage at V
Yes.
plus? So V plus will be nothing but 4 volt,
4
right?
volt. Yeah.
4 volt.
Now similar case, we are taking V1 as 5 volt and taking V minus is now, let's say 3 volt. Okay, now what would be the value of V positive?
It should be 8 volt
8
2
volt. Yes,
volt.
yeah, 8
8
volt
volt.
na.
because constant V1 voltage should be maintained.
Yes, this node, these two nodes having plus minus 5 volt always. So if this voltage go to 3 volt, this node must be go to 8 volt, so that the
Yes,
5
yes,
voltage,
Okay.
5
So the
voltage.
voltage difference will be always same,
Yes,
constant,
yes,
right?
this is the concept
Okay.
of ideal voltage source. Okay,
yes.
now in this second, case 2. Okay, so case 2, our, the polarity will be same, but our,
Take one different color for case two.
okay, let's say for case 2. Okay, this is for case 2.
That would be exciting.
Okay, yes.
Yes,
So now case 2, our V1 is minus 5 volt. Again, this case is always valid. So minus 5 volt will be always equal to plus minus V minus.
Yeah.
yes,
Now take V minus as minus 1 volt. Okay. Then
yes,
what would be the V plus?
It should be -4.
Yes, it should be
yes.
minus
It would be
4 volt.
-4,
So that this voltage remain minus 5 always.
-5 always.
Again another case. This is our 3 voltage. Okay. Now for this case, what will be our V positive at this node? So
That would be -2.
this will be minus 2. So that again the V1 remains minus 5 volt always. Okay. So this is the case. Okay,
Yes,
understood, right? So now for this case. Okay. So we are intentionally making, like, deliberately making this node as 0 volt.
Hmm.
So now
yes,
if this is 0 volt, this voltage is already fixed. What will be that? So if this is
yes,
5, so this potential must be 5. Okay, so this is our V positive. Okay,
yes,
this node is V positive and this node is V negative, and our V negative is fixed to always 0 voltage. So V positive
yes. This
must
is
be
bound to be zero
yes,
always.
yes, this is 0 volt. Okay, as this is connected to the ground. Okay, understood, right?
Yes,
So
Yes,
this
yes.
is
yes.
the two
Understood.
cases where, like, the ground, like what is the significance of ground? Okay, now another case, let's have a fun. Okay, go to the next page.
Yeah.
Okay, okay,
So this is our case 1, let's say case 2.
okay.
Now I have to find what is the value of I every case.
So in the first first picture, the two are grounded.
Yes.
Then draw another case where there is no ground.
Okay. There is no ground. Yes. Case 3 will be like this. So every case I need this I. Okay. Every case I need this I. Let's say case 1, case 2, case 3. Okay. What will be the case? And let's say
We,
we also we also want this V out. Okay. Let's say every case. So this will be more interesting, right?
yes, yes.
Okay. And let's say this Ix is nothing but a let's say 5 ut. Okay. Just a step of 5 ampere.
Okay.
So Srijan will tell, or I will. Can I continue?
Yes, I think I should try. Then you.
Okay. Okay. You try on. Okay.
Okay.
For first case. Okay. Let's.
So, so in the first case, uh, here is also grounded, and here is grounded.
Hmm.
So the V out for this case is should be 0 because
Okay. Yes. Yes.
two,
Exactly.
it is 0 volt.
Yes.
Okay.
So I think the current would be 0 here
Why?
because the voltage is not changing across the capacitor.
No. Let's
Am
see.
I right or
No.
not?
No. No. Actually, this is not the case
Okay.
here. This is
Okay.
ground and this is ground. So capacitor is not there, right? This is short circuited. So this is capacitor
Yes.
is actually dead here. Okay.
Yes. Yes.
Capacitor actually doing nothing. So we know that.
Doing nothing. Yes.
So the
Yes.
current through a constant current source is same, and like whatever the
Okay.
voltage across is, that doesn't matter, right?
That doesn't matter. Okay.
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 Yes. So
Okay. I get
the I will be Ix itself. Okay.
IX.
So this voltage
Okay.
can be infinite across it. This can be minus infinite. That can be zero.
Okay.
But the current will be same as Ix.
Yes. Yes.
Okay, right?
Okay. Okay.
That we
Okay.
have like learned previously, right? Starting of our video.
Yes. Yes.
So this is the case. Okay, this is our
Okay.
first case.
I is IX.
Yes, exactly. Now second case.
Okay.
This is case 2.
So second case also the I is a ideal current source.
So I will be
So
Ix. There is no doubt.
yes, whatever be the voltage, the current pushes the IX thing.
And let's say this is V plus, and let's say this is V minus. And across it, there is a V out. Okay.
Okay. So V minus is grounded. Then V plus is the voltage across the capacitor.
Then what would be the voltage across, like what will be the voltage at this node and at this node? So this node is fixed, right? So this is 0 volt.
Hmm.
Yes. Yes.
Then what would be the voltage at this V plus, this node?
Uh,
This
for
will be nothing but
capacitor.
I x by c
Yes.
into t, right?
Into T. Yes. Yes.
Basically the capacitor is integrating the current, and the is like
Yes. Yes.
as the
Capacitor
current
is
is,
indicating the current.
yes, as the current is constant, so this will be outside of the integration, and here we have only integration of dt, that is nothing but t.
T.
Okay.
So here we can use the like the t1 to t2 as well, if you
Yes.
want to
Yes.
do. Okay, if you want to do.
Whatever be the time, that is T.
Yes, that is t. Okay, and we are
Okay.
assuming that the it start from t equals 0. Okay, so that we are not writing t1 t2. So the v
Okay.
out will be nothing but let's write properly. Okay, so this will be ix, right? Ix is 5, so this will be 5 by c. Let's integration dt of t1 to t2. Okay, so this will be the
Yes.
final case, right?
Yes. Yes.
Now
Got
comes in case 3. What will be the case?
it.
And same similar case, the I will be ix,
IX.
it doesn't need any voltage like the like voltage across it to make the current is Ix. Okay, so this will be 5
Yes.
ampere. Okay, now what will be this case and this case? Like, can we directly comment what is the V plus and what is the V minus? Can we directly comment here?
No, the change should be dV, but we
Yes,
cannot comment
yes,
what is the V plus and V minus.
yes, we cannot directly comment of this V plus and this V minus, but yes, we can comment on this V out,
Yes.
because V out is the difference
So,
between this node and this node,
okay.
and the
So
same case.
for the
Okay.
current, if I write this, then it is this I should be the change in the voltage dV by T dV dt,
Mm-hmm.
right? Can I write this?
I will be CDVDT. Yes.
So this dV is the change in the voltage across it
Okay.
capacitance.
Yes. Yes. So this will be the equation, right? Again,
Yes, yes,
this will be the same equation, right? But
yes, yes,
here, in this case, V out was V plus itself.
yes,
But in this case, V out
It will be V plus minus V
and
minus, right?
yes, V plus minus V minus.
yes.
Mm.
V minus.
So V out will be nothing but V plus minus V minus, and this will be nothing but 5 by C integration T1 to T2 dt. Okay, so this is the case, right? This is clear, right?
Okay.
Write down the V out properly, V plus minus V minus for the third case.
Okay,
Yeah, yeah.
so this will be the same case.
Yes, yes,
Okay, or what can we discuss? Like the basic things. Okay, we forget the basic things while in our
yes, yes.
interview, right? In our interview.
Okay.
Hmm. So now what can we do? Achha, let's have a uh, okay. This is pretty clear. So like we are doing about the current case, and you can like
Yes,
shift to the voltage case accordingly. Okay, according to our discussion. Okay, make circuit yourself and vary the current across, like vary the current through a ideal voltage source, and draw the like try to calculate the uh, uh, voltage and the currents. Okay, like in this manner.
okay.
Okay, okay, can we talk about right now like the okay, let me do here. So what is the power? Okay,
Okay.
power and passive and active element. Passive and active element. So power is nothing but okay, power through a element is nothing but this, right? Let this is the element, and voltage across this is V, and current through it is I. Okay, uh, the direction of this current is like this. Okay,
Okay.
now what will be the power?
VI.
I into V. Okay,
Mm.
Yes,
and this will be positive, right? According
Yeah.
to our
yes. This
notation.
will be positive.
So now, if we can model a element like two port element like this voltage and this current, so there is a positive of power, right? So this device
Yes.
is called passive element. Okay, okay, this is called a
Okay.
passive element.
Okay.
So we know that RLC RLC is a passive element, right?
Yes.
Mm.
Actually, for active element, this power and the energy both are negative. Okay, for active element, if we model the element like this, and the power and the energy is nothing but what? Energy is nothing but power into time.
Yes.
So this, if this quantity, both of this quantity becomes negative, then the element is active element.
Okay.
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 Otherwise, if the power or the energy is positive, like in this manner, so that is called a passive element, like RLC.
Okay.
And we know that R is nothing but this, right? So let's say this is our I and this is our V. And we also know that, let's say VR, and this is IR. We also know that current entering to a node of a resistor is always positive, right?
Hmm.
So this is the case. Current is entering to this node, let's say A. So this A node is positive and the B node is negative. Okay. Current leaving the node. Okay. So same current has to be leave, right, from this B node,
Yes.
so that KVL should satisfy.
Yes.
So
Yes.
current leaving to a resistor, that node is positive, and the current entering to the node is positive, and current leaving the node is negative. Okay. So this is
Okay.
our VR, plus minus VR. But you will see, we know that. Okay, go to the next page. We know, and this is also called power dissipating device. Dissipating. Okay. Okay. Power dissipating device R. কারণ it dissipate powers in I square R form. Okay. Or V square by R
Okay.
form. Right.
Yes. Yes. Yes.
Yes. And RLC, you will see, if we analyze C and L, this is called storing element, right?
Yes.
Yeah.
And like storing element, and this is not storing element, not storing element. Like it cannot hold its previous voltage. Like the voltage or current through a resistance can change instantly, right? The
Okay.
voltage
Okay.
across a resistance or current through a resistance can change suddenly. Like we have, let's say, t equal to 2 seconds, we have a voltage of 2 volt. And here we have a t equal to 2 second plus, the voltage can be 5 volt across
Yes.
a resistance. Okay, so this is called
It can be
non-storing element.
instantaneous. Yes.
Okay, that the drop of the voltage across is instantaneous.
Yes.
But we know that the capacitor and inductor is a storing element. The capacitor stores the charge as a voltage, as a form of voltage V, and the inductor like store charges in the form of current I.
Hmm.
Like
Yes.
the voltage across a capacitor cannot change instantly, okay, until there is not a infinite current. So okay,
Yes.
I will tell the all the properties of a capacitor and inductor. Okay.
Hmm. So before that, I think I have a question.
Tell it.
So in the previous case,
Hmm.
uh, previous slide, you said that for the passive element,
Hmm.
the power is positive VI.
Yes.
So can is there any case that I can tell for the passive element it is negative VI power?
Negative BI means, okay, you can draw right here, page number 9.
Okay.
Okay, let me try your question first, right?
Yes. Yes. Maybe I am wrong. I am wrong, but I think I have this confusion. So if there is any passive element,
Hmm.
the current is entering here,
Yes.
right? So the voltage across it V. So
Write the
power across it.
write the polarity of this voltage.
Okay, 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 okay. This.
Okay.
For this case, we can write that is P is equals to plus VI,
Yes.
right?
Yes.
So, so I am asking you that if there is any case for the passive element, the P can be minus VI. Can I say?
Yes, yes,
Or
yes. Yes, this is the case for inductor, capacitor and inductor. Okay. But
okay, okay,
yes, so that I have written now. Let's go to page number 7.
okay,
I have written that for active element, power and energy both should be negative.
Okay, okay,
So similarly, power and energy both should be positive for passive element.
okay, okay,
Okay. So okay, let go move to page number 9. Okay.
okay.
Let's have capacitor. Okay. So we know that if there is a positive current, that is charging this capacitor, right?
Yes, 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 yes,
So this will be plus. So there is no problem.
yes.
But let's say we are giving a negative current here. Okay.
Okay,
We
okay.
can give it, right?
Yes, yes,
So then the power becomes powers become negative, right?
yes,
Yeah.
yes.
But
That is the case I am want to say.
okay,
Yes,
but
yes,
what about the energy? Energy is half into cv square, right?
Yeah.
yes,
So
Yes.
like
Well,
so there is a square term, right?
yeah.
yes,
So if we like convert it to I, there will be another I square term for this energy,
yes, yes.
so that the energy always positive for this A
Positive.
and C. Okay,
Okay, okay.
so that they are called passive element.
Yes, yes, yes.
Actually, this is very interesting, and student like may get stuck there. Okay, why it is called
Okay, okay.
passive element?
Yes, yes. That's the confusion. Yes, right. Okay, okay.
Okay, now go to the important thing. What are the properties of a capacitor? Okay,
Okay.
Yes, yes.
actually we are talking about ideal case. Okay, not about the practical case. What we have done in real circuit, like there the the yeah like like the capacitor may have 4 terminal, 3 terminal. So we are not going to consider that. Okay, we are going to
Okay, okay.
basic theoretical knowledge of a two-port capacitor, inductor, and
Okay, okay.
resistor.
We also note this thing
Okay,
for
yes.
solving any circuit.
So now let's we have a capacitor. So this is V plus, this is V minus, this is C. What is the V out? Let's say VC. So VC is nothing but V plus minus V minus. So these
Yes,
two voltage can be anything, but the VC should be this, right?
this. Okay.
Now, so now, okay. So I have said that this is a storing element. Storing element means the voltage remains same at t equals 0 plus, like 0 minus, and t equals 0 plus, until until the I, let's say this IC is not infinite.
Yes.
Is this clear?
Yes, yes.
Like if this IC is finite or 0, like 0 is finite, right? If IC is 0
Yes.
or some finite, then this always hold. Like the previous value
Correct.
is 0 minus, right? So the like the initial value will be hold by this capacitor. This is the property. Okay, let have an example. Okay, so that you will understand.
Yes.
Let have a capacitor. Let's say this is charged to 3 volt initially.
Okay.
This is 5 volt, this is R, and R is, let's say, 10k. Case 1, and case 2 is nothing but, now we have to find the VC. And I am telling the capacitor is a storing element, means if we have a like n term, okay, like n, like we have to find the, let's say, like in some nth time. So it will, what it will do, it will sum up the previous voltages, sum of the previous voltages with this nth voltage. Okay,
Okay.
so this is the like the storing capacity, right?
Okay.
Okay, like it will sum up all the previous voltage with this new voltage, and it will give the final voltage across it.
Okay.
Okay,
Okay.
okay, I will give some examples, it will be clear. Okay, no problem. Now in this case, Now if we draw the voltage output waveform with respect to time, and here we have also a voltage waveform with respect to time. So in this case, what happening? So this 5 is nothing but this 5 ut, right? Step
Yes.
input.
Step.
Now can you
Okay.
draw the VC here for this first case 1, Srijan? This is case 2. So
Okay.
basically I am drawing. So basically initially at t equals 0 or 0 minus, okay, you are doing, okay. Okay, do.
Okay. So VC is initially 3 volt.
Okay, this is 3 volt, okay.
So this is 3 volt. I think is it visible?
Yes, visible.
Yeah.
Okay. Okay. And the final voltage across the capacitor is 5 volt. I
Yes,
mean, after steady state, it is getting 5 volt.
yes, 5 volt.
So, it is like, okay, but the current is flowing through this resistance like this. So, I think it would be exponentially charged to the 5 volt.
Yes, so this is the case, right? So we can see that from 3 volt to 5 volt,
5 volt.
it is taking a lot of time and it will start charge to
Yes, yes,
exponentially, right? So it cannot,
yes,
it is not changing the voltage across it instantly from 3 to 5 voltage, right?
yes,
Hmm.
yes,
Because there is a finite current. So the initial current was 5 minus 3 by R. So this was the initial current,
yes,
okay, at this time.
yes, yes,
And the time increases, the capacitive increases also increases, so current become decreasing. So at steady state this
yes,
become open circuit, so current becomes zero. We all know that,
yes,
right?
yes, yes.
Okay, now
So
what
for the
about,
time being, the VC gets increased more and more, and the difference between the 5 volt and VC get lowered, and the current is zero
yes,
at
this
steady
is the
state.
another approach. Yes, this is charging, so this voltage is increasing, this voltage is fixed, so
Yes,
the current will be decreasing, right?
yes, yes,
Yes, this is the another
yes,
interpretation, okay. And we
Okay.
also know that at t equals infinite, t equals infinity, the frequency is zero, right?
yes,
So
Yeah.
if frequency is zero, the capacitive impedance is infinite. So this
Hmm.
becomes open circuit, right? So there is
yes,
no current. So
correct.
okay,
There is no current.
okay, yes, this is the interpretation. So now what about this case? Let plot here. Case 2. Previously it was having 3 volt, right? Initially.
Yes,
So
3
this is,
volt.
let's say, 3 volt. Now we can see that the at t equals 0 plus the capacitor is short circuited, right? Both this case.
Yes,
Capacitor is short circuited. So output is what? That was the, like, this was the case. Like if we draw there, so this will be the circuit, right? So this is short circuit, and here it acts as a 3 voltage source,
yes,
and this is 5 voltage. So the output VC becomes 3 voltage, okay.
yes.
But what about this case? Here
In
we
this
have,
case, there is no resistive path.
yes, so there is no resistive path, so it will be looking
Yes,
like this. So
yes,
this is our 3 volt, and this is our 5 volt.
yes,
Now, like, at this node there is two potential, right? 5 volt and 3 volt
yes,
at t equals 0 plus. So is KVL is satisfied or not? Actually KVL is violated here, right?
Yeah.
yes. KVL is violated here.
And so basically this KVL is violated because of why? Because the current at t equals 0 is infinite, because
Infinite. Yes, yes.
there is a zero resistance,
Correct,
right? Because I becomes
correct, correct.
5 minus 0 divided by 0, like there is no resistance,
Yes,
so this
yes, yes,
becomes infinity.
Yeah.
So if this is infinity, the current through the capacitor becomes infinity, then it can the voltage across is instantly. So it what it will do, it
Yes.
will jumps to 5 volt and settle down.
I bold. Right.
So
Yes.
this is the instant changing. Okay, Chandrima.
Yes.
Okay.
So this is the instant changing. The capacitor cannot change its potential across it until there is a infinite current. So here we can see
Okay.
that in this case, the
I
current.
think Amit, I think for next page you should do two graphs properly
Okay,
because
okay. So
for
okay, let
the
me do here. Okay.
latter audience will understand. Yes.
So this is for second case. Okay.
Yes.
So previously it was 3 volt and instantly it charged to 5 volt and then it settled.
Yes.
So this is called instant charging. Like the here, the capacitor cannot hold this property. Okay,
Hmm.
cannot hold cap properties. Okay, like we all know it can hold the previous voltage, but in this case this is not happening, right?
Yes.
This is the instant charging of a capacitor. Like it can changes its potential across it instantly. So this is the, like in this case the capacitor is not holding its property. Okay, this is the case whenever there is an infinite current.
Okay.
So I think this is very much understood. Mm,
Yeah.
then acha. So okay, let go to the time constant segment. Okay, for a RC circuit.
Yes.
Okay.
Okay, let there is another thing, some mathematicals. Okay, so now we know that the voltage across a capacitor VC of 0, like initial VC of initial and VC of present. Okay, what I have written in like few times ago. Okay,
Hmm.
but for a RC circuit, if we take output from here, let's say this is a Vx of step, then what will be the, let's say this is previously charged to let's say VC of 0 minus. Okay, VC of 0. Okay, now if we now tell what will be the expression for this case, we all know what would be the case. So this is the time function. So this will be nothing but,
Okay. 1 second.
okay, VC of infinity plus VC of 0 plus minus VC of infinity into e power t by tau, right? Okay, wait for decision. Okay, actually how this exponential comes, you all know. We will having a differential equation, right? Because we know that the I is nothing but c dvc dt, right?
Yeah.
And if we write kvl, so vx will be nothing but this ir, let's say this is ir, right? Ir
Hmm.
plus this vc. So now
Yeah.
if we replace this I with this, you will be getting a differential equation. Okay, now if you solve for vc of t, you will be getting this type of equation. Okay,
Okay.
okay, this is how the equation comes.
Okay.
Okay, and I am not going to write this differential equation like the solution of this differential equation. Okay, this is very basic.
Okay.
Here this tau is called time constant. Okay,
Right.
time constant, and this is nothing but here is rc, and the unit will be nothing but second. Okay, Okay, after doing some like the
Okay. Here's some problem.
okay, can you rejoin again? Sure, you can continue. Okay, okay, okay. Let's have some examples. Okay, to solve RC circuit and find the time constant and the pole concept as well. Okay,
Yeah.
okay. Let's go to the next page. So now we have seen that this RC circuit and this the time constant is nothing but RC, and this is a step. Okay, step of Vx.
Mm.
Okay. So now for a single pole system, the time constant is the like inverse of pole. Okay, so the pole location will be nothing but omega p will be nothing but 1 by rc.
By
Okay,
RC.
radian per second. So this is the pole concept. Now if we draw the Bode plot of this RC circuit, what will be that? So we know that the DC gain means this capacitor is open, right? And this is our V out. So our V out becomes V in, right? If this is V in, because there is no IR drop, right? So our
Yes.
circuit becomes this. So this is V out and this is our V in. So we can see that V out is equal to V in, right?
Mm.
So if we draw the Bode plot, Bode magnitude plot, this will be like this. Okay, let's say this is omega. So here the DC gain is nothing but V out by V in is our DC gain. So this is DC gain will be nothing but 0 dB, right?
Yeah.
Like this is 1. If we convert it into dB, like 20 log of 10 1, this will be 0, right? So this is our
Yes.
0 dB, and this will be our like at pole frequency the Bode magnitude plot falls minus 20 dB per decade. So the
Mm.
slope is 20 dB per decade, right? And this is the
Yes.
1 by RC frequency.
Yeah.
And similarly, if we draw Bode phase plot, what will be the case? Okay, so let me do in 14 number page. So if we do the Bode phase plot, so if this is degree, right? And this is omega. So we know that at at omega frequency the circuit feels like the transfer function feels minus 45 degree decade, right? Phase shift. So this will be
Mm.
like, so let's say this is minus 45 degree, and eventually at infinity frequency it goes to minus 90. Okay, so this is the phase plot of a normal first order
Okay.
RC circuit.
Mm.
Okay, so what can we do? So now have some example uh, in like time domain. Okay, to comment the output voltage of a circuit. Okay, so we will solve these two circuit as season is left us like for this discussion. Okay.
Okay.
Hmm. So we will be solving these two questions. Let's say 5 volt. This is our V in. This is R. This is C, and this is C. Okay, let's say C1 C2. Okay, so this will be more. So we will be solving another question like this. Okay, let's solve first. So we have to comment what will be the voltage. Like we have to draw the voltage versus time. Okay.
Okay.
So we know that at t equals 0, capacitor is short circuit, right?
Yeah.
So short circuit, if we do that, the circuit will be looking like this. And both of the capacitor are initially uncharged. Okay. There is
Okay.
no initial charges. So this is 5 volt and this is our V out. So we can see that here again this node voltage is 0 volt and this node voltage is 5 volt. So the KVL is violated, right?
Yeah.
So it means there is a infinite current.
Okay.
Actually this is the case, right? Because in this path at t equals 0 plus, this is a short circuit path, right? So the R is 0 here and this is also short circuit. So the R is 0 here. So some 5 divided by 0. So the current will be infinite, right?
Infinite. Yeah.
Srijan, can you continue? Hello.
Yes, yes. Continue, continue.
Okay, 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 okay. So well, we will be having
Yeah,
some
there is
good.
some problem with my laptop, so I left.
Okay.
Okay.
So we
Got
will
it.
be having some more problems. Okay. Okay. So let's start. So this is the case, right? So Srijan, I am solving this question intuitively in time domain. Okay.
Okay. Okay.
Okay. Let's solve. And we
Can
have
you
got,
elaborate the question again?
okay. So we have this circuit. Okay. Page number 15.
Okay. Okay.
Are you there at page number 15?
Yes.
Okay. So we have this circuit. There is two capacitors, C1, C1, C2. There the capacitance value is different. Okay.
Okay.
And we have a resistance R and we have a step input, and we have to comment the V out waveform without writing any equations. Like we have to solve intuitively. Okay.
Okay. Okay.
Okay. Now we are at this age t equals 0 plus. Okay.
Okay.
So we know that the t equals 0 plus, the frequency is infinite, right?
Yes.
So the capacitor is short circuited.
Yes.
So
Yes.
this is the short circuit path and this is the short circuit path, and resistance is nothing matter, right? Because the impedance, like the parallel impedance of two component will be the lowest path, right? So this is the zero impedance.
Yes. 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 Zero impedance.
So this path is zero impedance and this path is also zero impedance at t equals 0 plus.
Yes.
So the circuit will be looking like this. So the KVL
Yes. Yes.
KVL is violated,
Correct.
right?
Correct.
Because there is a zero
Yes.
potential here and there is a 5 potential here. So this cannot be possible.
Yes.
So actually
Yes.
there flows a infinite current,
Okay.
because this is a 5 volt and this is 5 volt and this is like the zero impedance, and here we have like the zero impedance, like if this is a like two path, so 0 plus 0 is always 0 impedance. So we have right I have right 5 by 0, this will be infinite current. So the capacitor property will not be hold here. So the capacitor at t equals 0 plus will change the potential across it suddenly, right?
Yes. Yes.
So now how they will like how the voltage, like how the voltage will be changing according to the capacitive divider rule. Okay.
Okay.
Okay, so now we can see that the voltage across V2 will be nothing but V2, or V out will be nothing but V2, or V out will be nothing but capacitor divider is nothing but 5 into C1 divided by C1 plus C2.
C1
Okay.
plus C2. Yes.
And what will be the voltage across this VC1? So this will be nothing but, okay, let me do the next page. Okay.
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 So VC1 will be, okay, let me draw the picture here clearly. Okay. Sorry, yeah. This will be this. So this is our VC1 and this is our V out or our VC2. Okay. This is the same thing.
Yes.
So this is our VC1 and this is C1. So the voltage across the capacitor C1, what will be the case? So this will be 5 into C2 by C1 plus C2.
C1
Okay.
plus C2. Yes.
And V out will be nothing but 5 into C1 by C1 plus C2. After that, after this is happening as t equals 0 plus. Now after that, the capacitive impedance is going to increase, right? And
Yes.
this is going to also increase,
Yeah.
right?
Yes. Yes.
So now the question is, the charging will be exponential or linear or instantly? Can we comment that?
Charging will be exponential.
Yes, the charging will be exponential because the currents become finite after t equals 0 plus. Okay.
Yes.
So we have conclusion that t equals 0 plus, the charging will be instantaneous. Okay. Instantly. Then the charging will be exponential. Now
Yes.
at steady state means t equal to infinity. So at t equal to infinity, the capacitor is open circuit, right?
Hmm.
Yes.
So the picture will be looking like this. So this is open, this is open, this is our 5, this is our
Yes.
V out. Then what would be our V out here?
V out is 5 volt.
V out is 5 volt because there is no current. So the IR drop is
Yes.
also 0. So this becomes a
0.
short circuit. So V out becomes 5 volt, right?
Yes.
Yeah.
So if we try to draw the waveform now, what will be the case? Now, what will be the voltage across VC1? Can we comment at t equal to infinity? Like we have find the V out at t equals infinity. But what will be the voltage at VC1? This becomes short circuit, right?
Yes. Yes.
So this potential is like this and this potential is like this. Same case. So the VC1 will be what? Zero, na?
Zero.
There is no
Yes.
higher drop. So this potential,
Yes.
like this was the VC1, right? This was plus and this was minus, right?
Yes. Yes.
And KVL also
VC1 is
has,
zero.
and KVL also have to satisfy, na? So 5 becomes 0 plus 5 at t equals infinity, because we have find that the V out will be 5 volt itself. So the VC1
Yes. Yes.
must be
Yes.
0, right?
Yes.
So now if we plot that, so instantly it goes to, okay, instantly the VC1 goes to 5 into C2 by C1 plus C2 instantly, okay.
Yes.
Okay.
Then exponentially it goes to 0, right?
Zero.
We are talking about this VC1.
Yes. Yes.
We have find that, right? And similarly it charges to exponentially at 5 into C1 by C1 plus C2.
C1 plus C2. Yes.
This is the V out. Then it exponentially goes to 5 voltage, right?
Yes.
So this is the solution and this is the way you should approach in the interview.
Yes. Yes.
Okay, there are many interpretations like KCL, KVL things, short circuit, open
Hmm.
circuit thing, exponential, linear or instant things. So you should like explain this way properly. So actually
Yes.
what
Yes.
we are saying that this both capacitor is charging to some voltages. Let's say if this C1 becomes C2 equals C. So both of these capacitor charges to 2.5 volt
Yes.
at t equals 0. And
Mm.
then this capacitor is discharging through this path, or you can say this
Yes.
path, and this capacitor is C2 is charging more towards this V in.
Yes. Yes.
So this is the like intuition behind this circuits, okay.
Okay.
Now let's have another circuit and Srijan will start the analysis, okay.
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 Okay,
Amit, for this case,
okay.
uh, can we write the time constant and
Yes.
the
Okay,
pole zero
let's
case?
have, okay. So time
Let's
constant,
complete it. Yes.
okay, yes, time constant. Okay, we will try to time constant and pole zero as well, okay.
Okay.
So to find time constant, what we will do intuitively, we make all the independent sources inactive, okay. Like we are not going to write KCL and KB and then find Laplace equation to comment on time constant or so on,
No,
okay.
no, no.
We are
Yes, yes.
going fully on intuition.
Intuition.
So this is the intuitive analysis. So all the independent sources are inactive. That means if there is a voltage source, this will be short circuited, and if there is a current source, this will be open circuited.
Open circuit.
And
Yes.
then we have to find equivalent resistance and equivalent capacitance. Then the time constant will be R equivalent time C equivalent,
Into
okay.
C equivalent.
So this is the way.
Yes.
Mm.
And to find pole zero, we will do the intuition again, okay, and we'll be doing the next part,
Okay.
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 Okay,
Okay.
let's find time constant here. So we have this circuit. So we have a voltage source here, and this is independent source, right? This V in, right?
Yes, yes.
So this will be short circuit to the ground, right?
Mm.
Now, what is the equivalent resistance here in this circuit? The R only, right? Like
Right.
there is
Yes.
only
Right.
resistance R, right? There is no other resistance.
Mm.
Yes.
And what is the C equivalent? We can see there is a two capacitor, and they both comes in parallel because
Parallel.
one node is
C1
connected
plus
here
C2.
and another node are
Yes.
connected in ground, right?
Mm.
Both of
Yeah.
Ground.
them. So they are comes in parallel. So parallel means they will be adding.
Yes, C1 plus C2.
Okay, then what will be the time constant? R into C1 plus C2.
C1 plus C2. Yes, yes.
So this
Correct.
is the case. Okay.
Okay.
Now go to the next page. But, so another thing, we have two capacitor here, right? What will be the order of the circuit? What is the order
It
of the
should be
circuit?
second order circuit.
This is the like you are telling this is a second order circuit, right?
But I think we have to write the transfer function for the order, right?
Yes, yes. But we are not going to do that. We can directly comment
Yes.
that. Is it a first order or second order or any order?
How?
Okay, okay. Good, good.
So actually we know that if we have a n number of storing element, so the order will be n order circuit. Okay.
Okay.
So
Yes,
here we have two storing element, right?
Mm.
So the order will be 2, right?
Mm.
Actually
yes.
this is not the case. I have written a wrong statement. This should be written like the following. There should be n number of independent storing element or independent state variables. Okay.
Okay,
State variables, independent state variables, n number of, then we can directly comment the order of the circuit is n. Back to the
okay,
page number 17.
okay.
Mm.
How, what is the
So can you
equivalent?
please elaborate what is the independent means here?
Yes, yes, yes. Independent means, let's say, okay, this is acha, for capacitor our variable is voltage, and for inductor our variable is current, state variables. Okay.
Mm.
Okay,
This is our VC1, right? And this is our V out. Now Srijan, if we make one of these V out or VC on, make like make fixed. So
okay.
5 will be VC1 plus VC2 or V out.
Yes, yes,
Now if we make this voltage fixed, this will be automatically fixed, right?
yes,
Due to this KVL, or or
Mm.
or
yes, yes,
or we can make it fixed, then it should be fixed as well due to this KVL.
yes, yes.
So we
Exactly.
have only one accessible terminal or accessible component
Okay.
here.
The other one is dependent on the other,
Yes,
right?
other one is dependent on the
Yes.
other. So that here,
Okay, okay. I
like,
got it.
yes, the effective capacitance is also, number of effective capacitance is also one, and the number of independent variable is also one for this circuit. So this is a first order circuit.
Yes.
Okay.
Okay. Actually, if there is a like n number of capacitance present there, so the maximum order can be that number, maximum, but it can be reducing, like can be reduced depending upon the state variable, like independent state
Okay.
variables. Okay.
Okay.
So if we have a 3 capacitor, the maximum number of order can be 3. Maximum can be 3, but
Yes.
like due to the circuit topology, it can be on as well. Okay.
Yes, yes.
So the order can be on and on as well. So this is the thing. Okay.
Okay.
Okay, let go to the pole and zero, right?
Okay.
Yes.
Okay. So pole and zero. Okay. Pole means we know that. So this is a single order circuit, right? Single order
Yes.
circuit or on pole system or first order circuit, whatever you can call.
Yes, yes.
Okay.
Okay.
Now we know that for a first order circuit, omega pole, like the pole location is nothing but 1 by time constant. We all know that,
Mm.
Yes.
right? So this will be nothing but
Yes.
1 by
R
1
into
by
C1 plus C2.
C1 plus. Yes, this is the pole location. Now intuitively find pole and zero here. Okay. So for pole, what we know, the input will be, all the independent source will be inactive, right?
Inactive, right? Yes.
And we have to find the equivalent resistance and
And
equivalent
equivalent capacitance for that.
equivalent
Yes, yes,
capacitance. And similarly, we will get the same thing, right?
yes,
And then the pole location will be nothing but 1 over R equivalent times C equivalent. And we have already find that. So this will be 1 by R C1 plus C2. Okay.
yes, yes.
Question comes, is there any zero? Like intuitively, you can
So
write Laplace domain transfer function, you will find there is zero or not. But we are not going to do that. We will see the circuit and instantly we will comment they are present as zero or not.
yes, yes,
So,
yes. You can
so
comment it.
I can see that there is a, so this is our Vin, right?
Yes,
So we can see that there is a two frequency dependent path. One is from here and another is from here.
yes,
So if we have a two frequency dependent path from input to output, so their
yes.
maximum chances they are have a zero. Okay.
Okay.
Okay,
And
okay,
actually there is. Okay. So if we have
okay.
two frequency dependent path from input to output, okay, like if we have a extra frequency dependent path from input to output, there must have a zero.
There must have a zero. Okay,
Okay,
okay.
like must like they are like maximum chance having a zero.
For
Okay.
maximum case, there is a zero. Yes,
Okay, yes, this is the
yes, yes.
case. Okay.
Okay.
And another thing, and if we do time domain response, if there is a certain jump across the capacitor voltage, that means they are definitely a zero.
Okay,
Okay, now back to the slide number 16.
okay.
So we can see that there is a certain jump, okay, at t equals 0 plus. So this ensure there must be a zero, right?
Okay.
Okay, understood. So this
Yes,
is
yes.
the like more like comprehensive learning than frequency domain.
Okay, okay.
Time domain is more real, right? We know that. So
Yeah.
Yes,
if
yes.
if in the time domain the voltage as t equals 0 plus changes instantly, so
Mm.
there is that ensure that they are present as zero. Now go to the page number
Yes.
19 again. Now we are like we have a conclusion that there is a zero. But what will be the zero location? For zero location, we know that there the V out will be 0 volt, right?
Mm.
Yes, yes. V out must be 0 volt.
So zero means the V out would be grounded.
Yes,
Then again we have to find the equivalent resistance and equivalent capacitance. So we can see that for this C2, one terminal is grounded in this fashion and another is grounded in this fashion. So
C2
this
is out of
C2
picture.
capacitor is out
Yes,
of the picture. So if we
yes, yes.
redraw the circuit, so this will be looking like this only. This is our V. Then what is the equivalent capacitance here? C1 itself. And what is the resistance
C1
here? R itself. So
R
what will be the zero location? 1 by R C1.
1 by RC.
R C1.
Yes,
Okay?
C1.
Yes.
Yes, yes, yes.
And another thing you can do for finding zero, go to the page number 20. Let's have a impedance of Z1 and impedance of Z2. Okay.
Okay.
Now for zero we know that V out will be zero, right?
Yes.
For which condition
So,
the V out can be zero? There is two conditions, right? If Z2
sir, if
becomes zero,
Z2 is 0, Z2 is 0, yes.
while Z1 not equal to zero. This is a one
Yes.
condition. And second
Yes.
condition is Z1 is infinite while
Yes.
Z2 is not infinite,
Yes, yes.
right? Now make, okay. So there is a C2 present here. Okay. What is the
Yes.
impedance of this? So this will be 1 over SC2.
1 by SC2.
So this will be zero to make the V
Yes.
out zero. So S is at
Yes,
infinite.
yes. Infinite.
So this is
But
not
we are not
possible.
considering that.
Okay, so
Yes, yes.
so infinite is not possible. So due to this C2
Yes.
capacitor, there is no zero.
Yes.
Okay, so this condition is not like applicable here. Okay,
Yes. Yes.
now do this case. So z1, so z1 is nothing but parallel combination of a r and c, right?
Yes.
So this will be
We
nothing
have to
but
make this infinite and calculate,
infinite.
right?
Yes, yes. So this will be infinite, right? So
Yes.
this will be nothing but 1 by 1 plus s rc1, right? So this will be infinite.
So
Are
the
you following?
denominator is 0.
Yes.
Yes.
So I am doing in the next page. So the this denominator will be 0, right?
Yes. Yes.
Okay, we are limited to page 20. Okay, so I am doing here. Okay,
Okay.
Okay. Okay.
so that denominator will be 0. So 1 plus s by
Yes. Yes.
rc1 will be 0. So s is nothing but minus 1 by rc1.
1 by r.
So here
Yes.
negative comes mean for stable circuit, like the both of the poles and zeros will be in the left of plane. Okay, so that
Yes.
don't don't worry about that negative sign. Okay, so this is the
Okay.
intuitive way, like there are so many ways you can like find pole and zero. Okay,
Yes. Amit, in the next day, we will discuss about this right half plane and left half plane cases.
okay. So I
Right.
think
In the
yes,
stability criteria.
yes.
That will be more exciting, I think.
Actually, for a passive circuit, this is very much simple. Okay, but if we go
Yes.
active
Yes.
circuit like transconductor level or MOSFET level, then the problem comes.
Yes.
Actually, basically for passive circuit, all of these poles and zero must be left of plane. Okay,
Yes.
for passive circuit, but we will be seeing that the for active circuits the pole can be right of plane, like the zero can be right of plane, and for real circuit the pole must be left of plane. We all know.
Yes. Yes.
Okay, so let ends here, right?
Okay. So when I left, I miss something?
Okay, 1 minute. So I am like stop recording, then I will tell. Okay, stop recording.
Okay. Okay.
Okay.
Okay. Thank you. Thank you, everyone.